Now, let me tell you what our philosophies are. I'm going to tell you about our philosophy, and I'm going to tell you what you can do to actually realize that philosophy for us. Our philosophy is that the best way to learn science is to do it. And no matter what you get passively from other courses, here you don't function passively. You're supposed to be creating the science that you're learning. And so that's a really important thing that we hope at the end of the course that you're going to feel that you've gained from it. The end result is that almost everybody gets exhausted by the time they leave, and that's unfortunate, but I've taught in a course here, so and I supervise the courses, so I'm constantly exhausted. So just remember that, I'm constantly exhausted. So we're going to have you fill out an online evaluation form after the course is over, within a couple of weeks. It's really important that you do that. It's important for a couple things. First of all, it's going to help the directors decide what they have to tweak in order to get it next year, make it better next year. Second of all, it's going to be a tool that I'm going to use when I go up before different boards that supervise the NBL and say, look, this is a great course, this is something we want in our family. Or, this isn't such a great course. I don't believe that's going to happen. I know the quality of the faculty in this course, and it's amazing. So, and I know that you're an incredibly competitive group. How many applicants were there? Something like 140 applicants, and of those 140, you guys were chosen. So that's an amazing, absolutely amazing ratio, because all those applicants were already selected to be in PhD programs or postdocs or established investigators somewhere, so they've already gone through a lot of selection. So we know it's going to be successful, and you're going to drive it. But please fill in that form to give us whatever guidance we need for the future. Finally, I have one other thing to tell you that you're going to get out of this course. The title is right there, but in addition to all the subject matter and the joy you have in doing the creation of learning the material, this is going to be an incredible networking experience that happens for all of our courses. So you're going to come out with a network of friends that took the course with you. You could say something through it with you, but actually really enjoyed it with you. And second of all, with the faculty. And I can't tell you how important that is to most students' careers, is that we're not in isolation. We're not walking scientists that create everything in our own heads. We always have a network, and this is just going to be another incredibly important network for you. And that's the way the courses are set up. Okay, now those are the advertisements. There are some concerns that we always have, and we want, and you all, when you agreed to be a student of the course, there was something on the bottom said, I read this form and I agreed to follow all the rules in it. Well, I bet that it's sort of like going into a motel and agreeing to their rules on the email or whatever else. You know, everybody says yes, and we understand that. That's why I'm giving some to Grace, some versions of this, and she's going to send it out again electronically in a day or so. It goes through things that you know internally, and there's no question that You're just going to automatically follow that. So let me give you some examples. We want this to be a really positive experience for everybody. That means that we really take equal opportunity as a very important goal. Everybody is welcome here, and nobody should feel like they're harassed. Second of all, we will do our best to help anybody who has any specific concern. So you can go to Grace, you can go to the course directors if you've got a concern, or you can come to my office. You've all been in contact with Carol Hamill. She's in charge of our student affairs, and she's in my office, and she will be glad to talk to you if you have a concern. We all live in a building called Homestead, which is about a block in this direction. It's like a Cape Cod shingle building, and we're on the first floor. And you just go in there and ask for education, or ask for Carol Hamill, and someone will direct you to our offices. Let's see, we have to take some things really seriously, like this is a small village, and they are, every once in a while, they take great pride in the 1,000 or so scientists and students that come here every summer. But sometimes they're saying, oh my God, what a place, with all the scientists around. So we have to be kind of respectful of the neighbors. Another thing is we have to be very firm on our drug policy and our alcohol policy. People have some catered events that are going to have beer and wine, and that's great. Please, when you're on campus, that's it in terms of alcohol use. If you want to go to the Captain Kidd, it's not going to be open for about a week, but there are a couple of other bars and restaurants around here. That's fine. But in terms of your campus life, remember we have to be not alcohol-free, but it has to be under controlled situations, and that's already been arranged in terms of parties for the course. Are there any questions?
The weather going to be warmer?
Well, of course, we have this idyllic warm sunny weather. No, the fact is that we're surrounded by water, and that means two things. And that means that we, in the spring and early summer in particular, we are about 5 degrees or so, or maybe 10 degrees cooler, I won't say colder, cooler than Boston, okay? That's just because we're surrounded by water, and water is an incredibly good temperature buffer. That also means, should you want to be here in October, you'll find this place absolutely beautiful, unless it's a hurricane. So I can't, but I will say that today's weather is a step in the right direction compared to yesterday. Right?
I agree.
All right, and I would like to promise it to be like this or warmer for the rest of your stay here, but I can't do that. Or I can do it, but I won't be able to deliver.
Okay.
So I'm going to hang around for, thank you guys very much for coming here.
John.
Yes.
Our assessment evaluator, advisor, 2 minutes?
Sure. As you heard, my name is Liz Ann DeStefano. I'm from the University of Illinois at Urbana-Champaign, and I'm the external evaluator for this project. This summer school is an experiment. This is the first time we're doing it this way. Lots of good thinking went into this. We had lots of calls and meetings about how to organize this. And so one of the things that we're very interested in doing is saying, does this experience work to help bring together this community of computer scientists, cognitive scientists, neuroscientists around this new discipline? So we're very interested in what happens here. And you will be getting a survey from us also, might be a little bit different than the one that Bill talked to you about, because we're very interested in the content and the types of experiences that you've had. We'll also be doing a focus group and some interviews next week to get an idea of what your experiences have been and suggestions for improvement. But even more importantly, we're going to be following you forward. So you're a part of a community now, and that community is not going to go away when the Institute ends. We're hoping to keep you together and to keep learning and collaborating in this space, so that one of the goals of the Institute is to create a new discipline, and in 5 years we're going to look back and say, is that happening? Do we have this community? Very exciting to be here in the beginning. I evaluate another project that they've just done their 6th Summer Institute, and some of the people that came to the first Summer Institute are now professors, and they're still collaborating with the people that they met in that first Summer Institute. So these can be very powerful, and we want to assess the power of this. So this is human subjects research. I'm an educational researcher. I'm a professor in educational psychology, and you are my subjects in this particular study. Because you're human subjects, everybody should have a paper like this near them, no matter who you are, faculty, TA, staff, no matter who you are, you should have a piece of white paper near you. Is there anybody who doesn't have this piece of white paper? Okay. This is a consent form for human subjects so that you understand that we will be collecting data during these 2 weeks and beyond, and that you agree to participate in this human subjects research. It's completely voluntary. By not agreeing, you will not be affecting your status with the Institute, but we would very much like you to participate. So if you could please read this and indicate at the bottom whether you wish to participate or not wish to participate in this research. The letter itself has contact information for myself and our institutional review board, so you may keep the top of the letter if you'd like, or I have some extra copies. But if you could all take a moment to read it and sign it, and then if you could fold it and pass it over to your left, then I will collect it. Thank you.
So, I'm Tommaso Poggio, and I'm using this because we are video streaming these classes and also recording them. So let me tell you about why you are here, and I want to start this by telling you, even you probably know a bit about it, I want to tell you about the Center for Brains, Minds and Machines, and then why the summer school. So the center was started officially September 2013. It's funded by NSF for the next 5 years, and we hope for the next 10 years. We are told it's also going to be the flagship program for now of NSF within the Obama Brain Initiative. So let me tell you briefly what the vision for the center is, what we did do in order to realize it, and the vision of the center is about the problem of intelligence and the belief that it is, at least my personal belief, is that it's not only one of the great problems in science, like the origin of the universe, or the nature of matter, or the origin of life, but actually that it is the greatest problems of all. If you can solve it, that's a very ambitious goal, or even if you can make some progress in it, then you can be smarter, you can make machines that help us think better, and you can solve more easily all other great problems. So these are good arguments why this is, a very important problem. And it may be the time to try again to make progress on it. One reason to be optimistic is just in the last 15 years there have been a number of systems that are more intelligent than us in narrow domains. For instance, Watson winning a Jeopardy against human champions. And before that, Deep Blue was winning against Kasparov at chess. The X-47B has landed on an aircraft carrier last year for the first time. It's a drone without a pilot, doing probably the most difficult thing that a human pilot can do. I think there are more drone operators in the U.S. Air Force now than pilots. And all of these systems are intelligent, although in quite a narrow sense, in their specialty. Other systems that are kind of intelligent, these are things we did in my lab 15 or 20 years ago, face detection, and now you have it in your camera, everyone doing a relatively good job of finding faces. You have systems that can drive a car. This is an advertisement by Volvo. There's a radar, yes, 60, and also a camera that detects cars and pedestrians. In the lab, this was done about 15, 20 years ago, but now you can buy a car and it does work. So these systems are getting in our life, and it will be a golden age for, apps of this type. More and more, many opportunities to do interesting things, to make money, but, none of these systems, this was, by the way, Mobileye, which is one of our industrial partners, the Israeli company making that system for Volvo and for other cars. Even this system can drive a car that is not intelligent in the sense of, mimicking a human being, camouflaging for one of us. It cannot really solve, for instance, a Turing test for vision and of understanding a scene, answering questions about the scene. So, what we think is that in order to make systems that are broadly intelligent like we are, we need another phase of basic research on the problem in the intelligence, like it was done 50 years ago at the time of artificial intelligence in 62 or something like that. But this time, instead of relying just on computer science, we can rely on the convergence, on the progress that has been happening over the last few decades in computer science, especially machine learning and cognitive science and neuroscience. And so, what we did in order to realize this vision is to collect a number of people from various institutions from all these disciplines. Neuroscience, like Ed Boyden and Bob DeSimone and Gabriel Kreiman, and cognitive scientists like Nancy Kanwisher and Dee Spelke, and computer scientists like Patrick Winston and Shimon Ullman and Leslie Valiant. And so we put together a team. I want to show you also our industrial partners, because these are some of the big companies active in the technology, in developing technology of intelligence, and then some of the small companies, actually there were more, but since we started the center, Google has bought 2 of them, so they're now. Just to make the point that, what we are doing is combination, I think ideal combination of basic science and important technology, important for commercial applications. It's kind of a great mix, and so with this combination of people and partners, what we are trying to do in the next 10 years is really to make some progress on this problem of a broadly human-like intelligence, in addition to narrow intelligence that is starting to happen. And for doing this, we have within the centers 5 trusts, 5 directions of research, each one under a trust leader. So, and each one answering one of the questions, or trying to answer, to make progress on one of the questions that you should be able to answer if you say that you understand intelligence, how it develops, how it is implemented, what it means to understand C, what it means to understand others. And you have George Tenenbaum, Trust 1, Gabriel Kreiman, Trust 2, Shimon Ullman, Trust 3, and Nancy Kanwisher, Trust 4. And the theory trying to unify this, or theoretical tools for unifying all of this, is, say, a 5th trust, which I'm leading. Now, in a sense, and this is what I think would be interesting for you to keep in mind, there is one kind of challenge which is common to all these trusts, and it is to make progress on developing a system that could start to pass a kind of Turing test for vision. So suppose you're giving a scene or a video, and then I can ask a number of questions about it. I can ask what is there, that's object detection, object recognition. I can ask a question about what is this person doing, that's action recognition. I can ask more complicated questions about social interaction. And each one of us can, up to a question like, imagine what may be happening in that scene. Tell me a little story. And each one of us can answer this question, rightly or wrongly. There is no machine. We don't know how to make a system that can do that. And so the overall goal of the center is to make progress on developing a system like this, which could answer this question, could answer them in a way which is consistent with what we know about humans, how they would answer to this question, what happens in their brain when they're looking at a scene like this, and they have to answer those kind of questions. So it's a pretty ambitious goal, and I don't think at all we're going to answer all of these problems and solve them, but progress on it, that I expect, and I think that would be quite important and significant, is to develop really models, theory, understanding of what happens in the brain when we do pass through this challenge, and how, of course, can reproduce this in machines. So we expect a number of outcomes from progress in this kind of challenge. One, for instance, is about machine learning. You can say that the last 20 years, a lot of the systems I showed you at the beginning, like Watson or the Mobileye system, are an accomplishment of supervised learning and powerful computers. And the current paradigm for supervised learning, which is quite successful in terms of practical applications and also in terms of a mature mathematical theory, kind of paradigm is n going to infinity. The more data, essentially big data, the more data you have, labeled examples, the better. You know, in the Mobileye case, they had teams in India labeling images, labeling cars, pedestrians, millions of images. Now, that's not how human children learn. You know, in order to explain what is a car to a child, you don't show image of a car, this is a car, this is not a car, this is a million times. You don't do that. And so I think the challenge is to understand how humans can learn from a relatively small number of supervised examples. So that's kind of a caricature and going to one. That's the challenge. So that's something that we can expect to understand better, answering the kind of questions that are part of the CBMM challenge. Now, I want to say, repeating what Lisanne and also Bill mentioned, is that what we want to do in order to achieve these goals is to, in a sense, to create a new field of science, a new area, this intersection between computer science, cognitive science, neuroscience. And this means creating a community. I mean, science, you probably realized it already by now, but science is very much a social enterprise. It's creating a community, it's creating friends and a network of friends, speaking the same language, being interested in similar things. And summer schools are a great way to do that. Molecular biology was started by Max Delbruck with a summer course in Cold Spring Harbor, the FAGI group, in '45. And computational neuroscience was started here in Woodsall by the next student of mine, Christoph Koch and Jim Bauer. So this is why we are here. You know, you, the students, are the first generation, I hope, of this new field of science. We still need kind of a name, but you know, it's the study of intelligence, and this is, in a sense, the first attempt to try to do again what artificial intelligence tried 60 years ago, to understand, to make progress in understanding and replicating intelligence in machines. So, the social enterprise that starts with would be together for 2 weeks, and so I hope there will be an opportunity to have a lot of interactions and discussions and ideas and fun together. That's big part of what it takes to develop a new language, a new approach to this great problem. Now, as I showed you, one important component in this convergence of disciplines is machine learning. And so today and tomorrow, and also part of Saturday will be about machine learning. And so let me tell you what we're going to do. We'll do mainly supervised learning, which is, as I said, the end going to infinite paradigm. So this is a caricature of machine learning. Machine learning is supervised learning, is this problem of trying to find an algorithm or a map or a function that learns to predict the correct Y from an X. So to predict an output from an input, you can think of these outputs and inputs as vectors. Usually the input X is a high-dimensional vector. The output Y is often just a binary number, could be a high-dimensional vector too. And you want to do this starting from just a set of examples. Like in the Mobileye case, it would be image 1, and is it a pedestrian or not? And so on. So you have a lot of examples, and you want to find this function that maps the input into the output. And we see that this is quite similar to old problems in mathematics of function approximations, interpolations, with some new requirements, because the key part here is not to be able to find Y for X you already know, that's trivial, but is to find Y for X you have not seen before, for new images. And so this is actually one of the things that I'm proud of. Steve Smale is a great mathematician, and this was a paper 13 years ago in the Bulletin of the American Mathematical Society that in a sense put machine learning into the mainstream of real mathematics as opposed to statistics and he had at the beginning this quote that is from a paper of mine, which says that learning is one of the key problems of intelligence, and that's the why we start this course with it. So as I said, the simple caricature of supervised learning is this, in which you know the value of a function. In this case, X is one-dimensional. You know the value of the function at these red values of X. And the problem is to predict, to extrapolate the value of the function at other points. And as you can clearly see, or see from this figure, it's somewhat arbitrary how you do that. You know, which kind of function goes through those points. So how can you really solve this problem? Turns out there are two very related problems in machine learning, in this kind of machine learning, supervised learning. One is generalization, is to extrapolate from the known values of the function to parts, to other values of X here, for which you don't know the values of the function. And people that have recently looked and put the foundations of theories saying under which conditions this is possible, several people, some of them are up there, Vladimir Vapnik, Leslie Valiant, and Steve Smale. And quite related to it is this problem that the same problem of learning, the same problem of interpolating a function among known data points is one of the problems that are called in mathematics ill-posed. And as we will hear from Mahadevan, an ill-posed problem occurs when the solution either does not exist, or is not unique, or it depends in a discontinuous way on the data, on perturbations of the data. All things that are true for the learning progress, or can be true, especially the stability one. So, let's look at ill-posed problems first, especially inverse problems, and then I will, and so this will be the next hour and a half. Okay, and then I will tell you about generalization and ill-posedness in the specific problem of learning. Okay. Questions? Any questions? Okay.
So, as I'm getting set up, a couple of housekeeping issues. So, the person who really helped us arrange everything outside NDL is Grace Joe, to that. I'd like to make sure that you know. Also, just so that you know, this is the pointer. Okay, anyway, so there are also a number of teaching fellows who are helping us, officially and unofficially. So I'd like to introduce them. Andre Barbu, Leila Ishik, Emily Macvicious, and Yasmin Meros. You can raise your hands and introduce yourself to everybody over here. So for the people who are essentially going to be, all the students over here who are going to be doing projects, they are your point people for the projects. And in fact, that leads me to the next point to be made, which is that according to the schedule, the description of the projects was actually planned for tomorrow, but because of the fact that this is a 2-week course, and you already heard Bill Resnikov, thank you, tell you that the only way to do science, the only way to learn science is to do it, so we're going to get started immediately, and therefore this afternoon at 2:30 right here, all the students please come back, and the PFs will essentially help you get acquainted with the project. I hope everybody got the email that we sent out a few days ago, presumably. Okay. The goal of that description is, of course, for you to essentially self-organize so that you can get some progress and then report to everybody else in about 2 weeks, in fact. And so please, of course, come here this afternoon. Also, I think there are people from very different backgrounds who've come to this school, mathematicians, computer scientists, cognitive scientists, psychologists, statisticians. And so because of these heterogeneous backgrounds, and given that much of the progress that eventually needs to be done will require quantitative methods. If you've forgotten the math or you need a refresher, Emily and the other TFs have kindly offered to essentially put together a math and a computation camp for you this afternoon. So following the project descriptions at about 4:30 again over here. There are a number of events which allow you to get to know each other through informal meetings like the one yesterday evening, like barbecue on Saturday, the outing on Sunday. But in addition, so that you also get to know each other in terms of research, we have organized a half day of presentations on June 3rd at 9 a.m. Please give your slides to one of the TFs, particularly, presumably the one that you're essentially going to work with through the term of the course. Make sure that there are just 2 slides, one introducing the question, one introducing where you are, so that we can essentially all hear each other. So I hope you'll be willing to do that next Monday or Tuesday. All right, so what I'd like to do for you over the next hour or so is to tell you a little bit about what Tommy just stopped with, which is the question of why we should care about inverse problems and how we are going to essentially think about this. And this is going to be a theme that's essentially going to be pervasive right through the course. And the reason is very simple. Everything that you, from even from the perspective of my lecturing to you, everything that you're trying to infer from what I'm speaking is based on partial information. You have some information associated with my voice, you have some information associated with my wild gesticulations, which will become wilder with time. You have partial information associated with the text that's there on the screen, and you're trying to integrate all that and essentially try and develop a whole. In fact, we think of science as the ability to start with the theory and make predictions, but in fact, it's almost always the other way around. You have some data, partial information, and you're trying to construct theory. So inverse problems are pervasive everywhere. Some of you have seen this, others may not have. And so this introduction, I hope, will essentially bring everybody onto the same page. So as I said, over the next some time, I'm going to go through a set of topics associated with inverse problems, and this is the outline for the next hour. I'll tell you about some simple and not so simple inverse problems. The not so simple one is, of course, as Tommy already pointed out, a very big part of learning, which is a very big part of intelligence. I want to tell you about the conflicting requirements that inverse problems essentially bring to the table associated with accuracy and smoothness. For example, if I wanted to essentially fit a curve through a bunch of points, perfectly accurate model would be a polynomial, which essentially has a degree which is essentially the number of points. But of course, it's going to be very non-smooth. And so there is this issue. If it's very smooth, I have something which is completely flat. If it's very non-smooth, it's fitting everything, and it's not very robust. So these conflicting requirements are things that we constantly have to deal with. And using a bunch of examples, I will focus on what is now fairly well understood, the idea of what's a general linear inverse problem. In order to solve that, I will recapitulate some aspects of matrix algebra. For those of you who've forgotten it, for those of you in a refresher, come back this afternoon, stop us. We're all here for 2 weeks. So this is going to be a bit of knowledge through the fire hose, if you will, if you haven't seen this before. So I'll first focus on a deterministic framework and introduce, for those of you who've not seen it, very quickly, and refresh for those of you who have, the idea of solving these problems using singular value decomposition. Then focus on the idea that these sometimes conflicting requirements of accuracy and smoothness in the context of these inverse problems which tend to be ill-posed in a way which I'll make very precise in a minute. We have to look at regularization, and I'll tell you about a famous regularization which is about 40 years old, due to Russian mathematician Tikhonov, all in the deterministic framework. And then I'll close by telling you about a probabilistic framework for doing exactly the same thing. And again, as I said, this is going to be something that you're going to see again and again through the next 2 weeks in multiple different guises. Okay? Much of what I'm going to tell you, in fact, can be found in a very nice online textbook, because this is a very introductory lecture at this point, and here is the website. So I should also tell you all these slides will be available to everybody in the course via the Dropbox or through some other mechanism which will allow us to essentially communicate. Also, I should say, please stop me whenever you feel fit. If I'm going too fast, I'm not going to be able to speed up, but I can certainly slow down. All right, so onwards then. So inverse problems are not new. Inverse problems have been around for a very long time, and I'll give you an example in a couple of minutes. As I said, much of science can be thought of as inverse problems. Given data, what kind of theory should you essentially construct? But in a more humble pedestrian framework, inverse problems are associated, for example, in physics, which was where they first started to appear. The idea of scattering theory, the idea that if I have waves which are essentially moving past an obstacle, I essentially pick up the scattered wave field. I want to now try and construct the obstacle. How do I essentially construct that? In quantum mechanics, I have a scattered wave field. Can I construct the potential? In classical wave propagation, in radar, for example, can I construct the obstacle which essentially scattered the wave field? Geophysics, essentially the same problem, worth a lot more money than in physics, because if I can essentially prospect using seismic or electrical signals, I should be able to tell you something about whether there is gas, there is oil, what the density of rocks is, and so on. So again, I have a wave which is essentially impinging on a medium. I don't know what the medium is, but I'm essentially now trying to recover from the signal that's scattered from the medium some properties associated with the medium. Same kind of problem in biology. Instead of using acoustic waves or light waves, you use X-rays, you scatter a molecule, you want to try and understand what its structure is. So many of these problems have the sense of reversing what you normally do, which is given a wave, given an obstacle, find out what the scattered wave field over here, given the scattered wave field, find out what the obstacle is. Something that you're going to hear a lot about, something that many of you are familiar with already over here. People talk a lot about fMRI, the ability to essentially try and map activity in the brain, but everybody over here also knows, even though we like to forget, what we're really mapping when we're essentially looking at fMRI is blood flow, and trying to understand from that how neurons are firing is an inverse problem. It's a very hard problem. We don't quite know how to solve it. We are trying to essentially make guesses. Okay? In a different setting in engineering, often we are fitting models, we're trying to deconvolve images, again, an inverse problem. So what are inverse problems? Very, very general setting, which will become more and more clear. So given that there is an image, for example, in front of me, all of you, there's an operator, which is my lens, my retina, and so on. I get some data, which is essentially going up to my brain all the way from V1 to V6. There is some noise. I can essentially ask what the direct problem is, or I can ask what the inverse problem is. So the direct problem is, given the object, give me the data. The inverse problem is, given the data, please give me the image. And here is a description which I like very much, which I'll just read out to you. Two problems are inverses of one another if the formulation of each involves whole or part of the solution of the other. And what is direct and what is inverse is essentially purely historical often. It's not really something that is set in stone. The better studied one is typically called the direct problem. The poorly studied one is called the inverse problem. All right? Okay. So the direct problem over here, as I already told you, is given F, find D. The inverse problem is given D, find F. And A could be a linear operator, A could be a nonlinear operator, there could be noise which is additive, there could be noise which is multiplicative. So there's a huge variety of phenomena which fit into this innocuous looking equation. Okay. In the context of things that you're going to see over here is a classic one. The classic one is trying to understand images from scattering. And if I'm thinking about now light and how light interacts with the body, a simple question that one can ask is, given the shape of the body, can you describe the shadow? Very well defined. You give me a body, you essentially use ray optics, you have a light field essentially propagate so that it interacts with the body, you can construct the shadow. The inverse problem is characterizing shape from shadow. And immediately you know very, very well that this is ill-defined, ill-posed, and the reason it is ill-posed is if I have a concave body, the shadow will always be convex, and so there's a problem. Okay? In fact, I think this is probably the oldest inverse problem there is, because I read a description in the literature that Aristotle thought about this problem of characterizing shape from shadow in the context of asking whether the shape of the earth was that of a drum, a circular drum, or was that of a sphere? Okay? I will not read out the entire description except to point out that in order to solve this problem, he had to have multiple different pieces of information. It wasn't sufficient for him just to get the shadow of the Earth and the Moon, which would be a circle if it was a long drum, but it would also be a circle if it was part of a sphere. But in addition, he recognized that essentially if I move from one place to the other on the Earth, the celestial map changed. And in addition, he recognized that in fact, when I moved from one place to the other, bodies always fell the same way, towards the center. And using these additional pieces of information, he was essentially able to deduce, or he thought he was able to deduce, that it's more likely than not that the Earth is a sphere. It took a lot longer. And so again, already in this very simple example, you see that you're bringing in information from different bits in order to essentially build what you actually know from facts. So the facts are the shadow is a circle. The other bits of information that you have are beliefs or some sort of confidence in whether or not the particles fall centrally at all locations, whether or not the celestial map essentially changes from one location to the other, and you're trying to build in different parts of your sensory input to essentially create a model or to create some view of what what the shape is given that you essentially got shadows. Okay. All right. So starting with that, in fact, you can essentially try and describe a whole series of problems which are inverses of each other. One is well-posed and the other is ill-posed in a way which will become clear as soon as I give you the first example. For example, in arithmetic, if I multiply a number by another small number, that's a very well-defined problem. But if I essentially reverse the question, instead of multiplying AQ by A, I actually ask what happens if I essentially divide F by A, and A is a small number over here, then you know that that's a very badly defined problem, just from experience, because if I essentially divide by a very small number, any small change that I make in that small number get amplified. Okay? So in arithmetic, multiplication is well-posed, division is ill-posed. You change that simple problem, instead of multiplication by a number, by multiplication of one number by another, multiply a vector by a matrix, you have the generalization to linear algebra, and we'll spend a fair bit of time on that. Again, linear algebra, multiplying a vector by a matrix is well-posed, dividing a vector by a matrix is extremely ill-posed, potentially. And the reason it's ill-posed is because the matrix may not be square, and even if it is square, it may have eigenvalues which are very small, and for either one of these reasons, essentially you're going to have lots of trouble. Okay, so you see an example in arithmetic, you see an example in algebra, and of course you see, naturally, you want to move further. There's an example from calculus, and also life, I would claim. In life, differentiation is ill-posed, and differentiation is bad. And integration is well-posed, and integration is good. Integration always smooth, and one of the things that we're going to do with all of you guys is to essentially integrate. Okay. So what has all this got to do with brains, minds, and machines? Tommy's already said that. I'm going to essentially tell you a slightly different version of that. If I'm thinking about how we respond to what's happening in the world, we get sensory input, which is proximal, and we are trying to essentially use some computation or some set of computations in our brain to try and get perception. Okay? I get input from vision, I get input from olfaction, I get input from movement. I'm trying to put all that together and say, I understand now, taking all these things together, this is the person, and that person is defined in terms of all these different sensory inputs. And in fact, I like this view, which many times before, and it's worth emphasizing, that every problem in physics, if I essentially turn around, becomes a problem in perception at some level. So for example, in physics, the problems are associated with understanding how light interacts with matter, and the inverse problem is the problem of vision in psychology, in neuroscience. In the context of mechanics, forward problem, Newtonian problem is given initial conditions, given the forces, please tell me how the bodies move. The inverse problem in neuroscience is associated with movement, trying to understand by basically asking what happened in your brain, what happened in terms of planning, given that you moved around in certain ways. Olfaction is the inverse problem of hydrodynamics, because hydrodynamics tells you the forward problem. Given a concentration of a molecule, how does it essentially change as a function of space? How does it change as a function of time? The inverse problem is measure the concentration and please tell me something about where it came from, when it came from, how long has it been around. And in all these problems, inverse problem, you typically have partial information and you want to essentially determine the object. And the reason you want to do that is because you can do that, you can classify, and of course you can compress. And again, this is a theme that you will see right for the next couple of weeks. Okay, so I want to now give you two or three little examples. The first one is an example just in calculus. The second one is an example from numerical analysis. And then the third one essentially generalizes these ideas to focus on what the direct and what the inverse problems are, to sort of emphasize the point. So Newtonian mechanics, we have, for example, the mass times acceleration is a force. And if I'm given initial conditions for the position and for the velocity, and I'm given the force, then I can essentially solve the problem forward. Please tell me what the trajectory is. You give me some initial conditions, you give me the force, and I'm done. So the direct problem, the problem of integration, the smooth problem, the well-posed problem, is given the force or the acceleration, find the displacement. Easy to do. We learned this, and we've learned this for many, many years. The inverse problem is, give me give me U, find Q, right? So given the displacement, find the force. And you immediately know that this is not nice, and the reason it's not nice is because essentially every time I differentiate, I start to make errors. And I make errors because the differentiation is essentially going to be dependent on what the smallest window that I take for time, and I have to divide. Every time I differentiate, I have to essentially take position at one point, position at a different point, divide by the distance or the temporal variable time step, and that becomes very, very bad. And I'll give you an example completely quantitatively without essentially going through anything more than what's written over here. So for example, if I consider a potential U and I add to this function which seems innocuous. I haven't defined what n is. N is just a number over here, U of t plus cosine n t times 1 over n. If I differentiate this twice, I get Q is a Qn, which is function of n is Q of t minus n cosine n t. And you immediately see that as n becomes larger and larger, Un approaches U, so Un is the approximation to U. Un approaches U, which means the solutions are well behaved, but Qn and Q diverge from each other. Because as n goes to infinity, the Q's become worse and worse. And you see this transparently because unlike in the forward Newtonian mechanics integration problem, where things are smoothed out as I integrate, if I have a function which has jumps and bumps, I integrate things out, everything smooths. But if I differentiate, it becomes worse and worse. And here is a fantastically simple pathological example where the function converges perfectly nicely as this parameter n goes to infinity, but in fact, the quantity that I'm interested in, the acceleration, diverges. Okay. So building on that simple example, we can now construct this idea, which goes back to Hadamard, of what a well-posed problem is. And it doesn't necessarily have to be a forward or a backward problem. It's just a question of well-posed or not. Tommy alluded to this a few minutes ago, and I want to emphasize the first problem, the first question that one needs to address is if I give you an equation, an algebraic equation, a differential equation, doesn't really matter what, linear algebra equation, first question is there a solution? Second question is, if there is a solution, how many such solutions are there? And the third is the question of whether the solution is stable. So small changes in my initial conditions or small changes in my data, do they lead to large changes in the solution? If all three of these are true, that is to say, you have existence, you have uniqueness, and you have stability, and stability in this case means continuous dependence on data, then Hadamard told us that the problem is what's called well-posed. Well-posed in the sense that if I give you now this differential equation, algebra equation, or in the context of perception, I give you a set of sensory inputs, can I essentially deduce the object from which the sensory inputs are coming? If all these three conditions are satisfied, the answer is yes, I can do it, and I can do it uniquely, and that's great. If any one of these is violated, the problem is ill-posed. That was Hadamard's contribution from almost 100 years ago. In 1902, he published a very beautiful paper, essentially where he described this. Of these, the one that we're going to be worried about the most is the last. Okay? And the reason we're going to worry about the last one the most is because I'm thinking about linear equations, which is going to be the focus for today. We're going to start thinking about nonlinear equations and nonlinear ways of trying to invert problems later on. In linear equations, existence is almost a given. Not quite, but it's almost a given under conditions which I will explicitly indicate in a few minutes. Linear equations, if I have solutions, they're unique. Definition. This is going to be the scorpion sting. Okay. This is going to be where things are going to become difficult because it's no longer clear. It will not be clear, and I'll show you why. I've actually shown you why in this very simple example already, that you don't necessarily have continuous dependence on the data. That is to say, if I invert the problem, I'm going to have multiple ways of interpretation. In vision, for example, the whole idea of illusions essentially is associated precisely with that, because I get certain projections, and those projections are not sufficient for me to essentially extract or recover the object from which those projections came, and so you get tricked. Okay, so how do we solve these, or can we solve these? So it took another 50 years from Hadamard to Russian mathematician and his colleagues, Nikolai Tikhonov and Arsensis, who in the 1940s and 50s recognized that even though problems are ill-posed, you can actually make progress, you can essentially start approximating solutions, and I want to tell you about that after I give you the second example. And the second example is more of a numerical example rather than an analytic example, but it still makes the same point. So how, for example, if I'm given a set of points associated with how a function changes in time, how can we estimate the slope? It's an obvious question that comes up in the context of vision, where I'm essentially trying to detect differences between light and shadow. It comes up in motion, where I'm essentially looking at the body which is moving past me. In all these problems, I have to essentially calculate or estimate gradients. And so there's a very basic question that comes up is, if I want to calculate gradients, I have to estimate the slope. And I'll start with a graph which is essentially showing you what, for example, might be input into your senses of some stimulus. So the solid line is what it should be in an ideal world, and on top of that has been superposed some noise. Okay? And what you're given is the sum of these two, which is essentially indicated in red over here. So I have some noisy data, and generally noise is associated with what is happening at high frequency, short wavelengths. And so what you want to do is to try and extract from this some measure of the slope. Okay? So you have high frequency noise superposed on low frequency data, and if I want to try and estimate the slope of the function, the first question that you've got to ask yourself is, how do I sample? Okay. Because I'm not going to be able to get infinite sampling. I'm not going to be able to get the value of the function at every point in time. So I have to first ask myself, how frequently should I sample? And based on that, I have to ask myself, are there optimal ways of sampling? If I don't sample well, it's useless. If I basically sample 2 points, I'm never going to be able to capture even the low frequency content. If I sample too strongly, I'm going to tell you immediately, then I'm going to be trying to overfit, because if I sample too strongly, I'm going to pick up every nuance of this high frequency information, and then I'm going to make a mistake because the slopes are going to change enormously. Okay? So again, there is this very simple question which we're going to I hope we'll come back to over the next a couple of days when we think about questions of sampling. There are different views and different ways. There is a classical view that says that if I have frequencies which are bounded, so as long as the signal has an upper limit above which there are no frequencies, there is a theorem which goes back 75 years ago to a mathematician, Nyquist, who said that in fact there is an optimal rate. But more recently, there have been very, very nice views of the sampling problem which say that in fact I can get away with a lot less. The Nyquist view is the pessimistic view, if you will. A more modern view is the optimistic view, which says that in fact most functions are fairly well behaved, and so I don't have to sample all that often. Most functions in particular associated with natural scenes in vision, natural movements in natural motions in movement, and so on and so forth. Okay, I've already told you that differentiation is inherently unstable and noisy, and so if I actually started with noisy data, let me call the noisy data sampled at point tk, sk, which would be the true value of the function plus some noise. We are trying to estimate the slope. So naively we would say the slope is just the difference of the function at two particular points, tk and tk plus 1, at which I've sampled, divided by delta t, and if I essentially use and recognize the fact that the approximation to the function essentially has noise built in, I can rewrite this as f of tk plus 1 minus f of tk over delta t plus epsilon k plus 1, the noise at time tk, minus epsilon k, the noise at tk, divided by delta t. And the problem is that as I make my sampling narrower and narrower, as delta t becomes smaller and smaller, this becomes better and better, but this becomes worse and worse. Okay? So it's a very simple example which says, now I have a problem. I have a problem because you may think that to become more and more accurate, I reduce my sampling time, increase my sampling frequency, but if I have noise, eventually it becomes worse and worse. It becomes worse and worse precisely because of the noise. Okay, so if you were trying to accurately estimate the slope, you might say, what I really need to do is if the actual slope is dk and my approximation is this quantity, I just minimize the square of the errors. That's a very natural thing for you to tell me. But this is going to become worse and worse because you'd say delta t becomes smaller and smaller, and as delta t becomes smaller and smaller, this quantity which you've forgotten about, which you have no control over, essentially starts to diverge. So if you are solely thinking about accuracy, increasing the frequency of sampling makes things worse and worse. On the other hand, you'd say, we hope, and hope is what drives, I think, all of us in science, certainly the first thing in the morning. If I didn't have a hope of trying to solve the problem that I was starting out to do, I'll never succeed. So our hope is that, in fact, there is some underlying signal over here, and if there is some underlying signal, maybe I want to essentially balance this competition associated with trying to maximize accuracy with another trend, which is to essentially look at smoothness. Because I'm hoping that there is a real signal, and if there is a signal, then there is an underlying smooth quantity below, and therefore I want to essentially now worry not only about accuracy, but about smoothness. And this is the idea that Tikhonov essentially told us how to characterize and quantify, and the idea is instead of now minimizing just the accuracy, maximizing the accuracy, minimizing the square error, you also add a contribution, and the contribution over here is your approximation for the slope at time tk plus 1 minus the approximation of the slope at time tk. Why? Because if I do that, then I'm allowing the slope to vary, but not too strongly. Okay? Effectively, this is looking at the derivative of the slope. The derivative of the slope is essentially moving around rapidly, so the acceleration is very, very large. That's bad. It's unlikely that I'll essentially see a solution like that. But when I say that it's unlikely, you've already made a hypothesis. You made a hypothesis, you've said that there is a prior, and the prior is that somewhere under this mesh, there is a signal. That's the hope that drives us. And so we're essentially saying, maximize some combination of accuracy and smoothness, and this parameter alpha is what essentially controls how much I'm weighting the smoothness compared to the accuracy. As alpha becomes larger and larger, if alpha becomes infinity, minimizing this, who cares about this? Because if there is even a small change in the slope, you're going to penalize it. And so what are you going to get? You're going to get essentially approximating that complex curve, which is a straight line. But as alpha goes to 0, you suffer, because then you start to pick up the jitter. And so alpha is a filter, or alpha plays the role of a filter. How much am I willing to pay attention to the high frequency components compared to the low frequency components? Okay, so there's a little example, and I'm really sorry that it's not showing up as well as on my screen. So this is an example where I have this little function which has a linear part, f of t is proportional to t, and an oscillatory part. That's the actual derivative. You add some noise and you try to reconstruct the function by minimizing this quantity. And as alpha goes to 0, you do a disastrous job because of the noise. As alpha becomes larger and larger, for some optimal value of alpha, you're doing, for example, over here, alpha 10 to the minus 2, you're doing a reasonably good job. But as alpha becomes very large, exactly what you expect, you just replace the whole thing by its average. Okay? How can we now quantify this in a more general setting? as I said, please do stop me, right? If for any reason whatsoever, even if you want to take a break, there's a majority, then I will. All right, so I want to now generalize these two examples from an analytic perspective and from a simple differentiation perspective now to asking how we should think about inverse problems, linear inverse problems, and linear inverse problems I can always couch as matrix problems, because any linear operator I can discretize, and if I discretize, I can write it essentially as a matrix. Okay, so my linear forward problem would be, given F, given A, find D. F is an image, A is a measurement matrix, or a projection, and D is data. Forward problem is F is given, find D. The inverse problem is given D, find F, which involves the inversion of a matrix. I could have noise, and I'll come back to that in a while, but for now I'm going to focus on the case when I don't have noise at all. I already told you that there are potential difficulties if my matrix is not square, and in general won't be square, so I'm going to essentially tell you, just for notation, that D is an M by 1 vector, A is a rectangular matrix, M cross N, a dimension, and F, of course, by construction, then must be a vector which is N is 1. The rank of the matrix is R. The rank of the matrix, if it's a square matrix, is the number of non-zero eigenvalues. If it's a non-square matrix, it's associated with the non-zero singular value, which I'll essentially refresh for you in a minute. The boring problem, the one that all of you certainly know how to solve, was the one in high school that was taught to you where M was the same as N, and M and N were also the same as R. So you had a full rank matrix, which was square. So basically I have a set of simultaneous equations, number of unknowns is equal to the number of equations, and no equation was linearly dependent on any other. So that means it was full rank. Okay? That's the boring problem. And so we're going to immediately forget about that, because you know how to solve it. The interesting problem, the real problem, is either when M is much less than N, and I'll come back to the condition on R. So if M is less than N, then it potentially could be underdetermined, because I just don't have enough equations for unknowns, or if M is greater than N, in which case it would be overdetermined. I have more equations than unknowns. How can we essentially solve either one of these? I'll come back to this later. I'll focus on this for now. This is a more tractable version. This, in some sense, if it's underdetermined, I have a lot of freedom. Solutions potentially could be non-unique because I have more unknowns than equations, so I can arbitrarily start throwing out some equations, or equivalently, I can zero out some of the variables. And this is a whole field of signal processing which has exploded in the last few years under the guise of what's called compressive sensing, matching pursuit, and so on and so forth. But for now, let's focus on the case when the number of equations is more than the number of unknowns, so I have overdetermination, which is typically what's going to happen, for example, every time you try and fit a line through a set of points. A line has basically two quantities which describe it, a slope and an intercept. I have a whole number of points. I want to fit it through. What do? You minimize the error, or the least square error. So I want to now formalize that question, because that's essentially the heart of these inverse problems. And I want to formalize it by essentially asking that we solve this equation, D is equal to AF, we invert A. There are two ways. One is to generalize the idea of an inverse. The inverse of a square matrix we know how to compute. The inverse of a rectangular matrix, there is something called the generalized Moore-Penrose inverse. If you've seen this, then you know what I'm talking about. If you haven't seen this, look it up afterwards. Okay? I won't tell you about that. I'll tell you an equivalent and a very powerful computational approach, which is to recognize that for any matrix A, rectangular matrix A, there is a theorem which says that I can always rewrite that matrix A in terms of what is called traditionally a singular value decomposition, which is a product of three matrices U times sigma times V, where U essentially has for its columns orthonormal vectors, which correspond to the left singular vectors, or they're also called the data space. And the reason they're called the data space is because it has dimensions of M times N, M, and the data has dimension M times 1. So essentially, it's the space in which the data lives, if you want, with respect to which I can essentially express everything using U. Sigma is a rectangular matrix. So U is a square matrix, B is a square matrix, sigma is a rectangular matrix. Sigma is a rectangular matrix which has a certain number of non-zero diagonal elements. Everything else is zero, including a block which is completely zero. And the number of non-zero elements R is essentially the rank of this matrix R. And then V is another square matrix, and it corresponds to what's called the right singular vector, or the image space. And the reason it's called the image space is because it's operating on the image. Because if I write down A times F, V acts on F. So that corresponds to the image space. Okay? So in terms of this singular value decomposition, which I hope all of you are familiar with, and if you aren't, come and talk to us later on, we can essentially write down a solution formally and actually quantify how we should invert this matrix equation D is equal to AF by trying to minimize what's called the L2 norm, or the Euclidean norm. And here is the formalism. So it basically says the least squares idea is to find this approximation F, which is the solution of the following optimization problem, which is the argument associated with minimizing this norm D minus AF. Which norm do we pick? Typically what's picked is the 2 norm, the Euclidean distance, essentially. Equivalently, geometrically, what we're trying to do is to find the size of the sphere in which the points would fit, so that the center of the sphere is as close to all points as you possibly can have. That's the geometric interpretation of the least squares problem. How do we do that? We do that by expressing A in terms of its singular values, and then rewriting this equation D minus AF, or equivalently the norm, by essentially writing D minus AF squared can be written down in terms of singular vectors, the left singular vectors, the right singular vectors, and singular values. So this is a little bit of tedious algebra that I have to be able to at least tell you about, show you, and you can work through this later on. D is the data, and D must be represented in terms of the left singular vectors which correspond to the data space. So I project the data onto the left singular vectors. That's my projection. And then times the singular vectors themselves. That's D. And A is the singular value decomposition that I've written down over here. Singular values multiplied by the left eigenvector, left singular vector times the right singular vector projected on the image. Okay? This is this. Yeah.
The only regularizers that I ever see people use are L2, L1, or L0.
Yeah.
Is that for any reason besides like computational or analytical?
Short answer is no. So L2 is good in certain situations. It's very bad in certain other situations. Again, if I think about trying to fit a set of points with a line, if I have outliers, then L2 is a disaster, because the outliers essentially control everything. And so then you would say, maybe what I want to do is not to go to L2, but to go to L0. Basically, I just start throwing out things. So the variables are either 0 or not 0. But L0 turns out to be non-convex. So this is going to very rapidly become a technical discussion. And if it's non-convex, you don't have any good methods to do that. And so there are some theorems which show that almost always you can replace L0, minimizing the L0 norm by the L1 norm, and minimizing the L1 norm allows you to essentially use methods from convex optimization. But the short answer to your question is they are all associated with computational ease rather than anything else. Okay, so I want to minimize this norm, and if I just write it out explicitly, I can write it out in terms of 2 parts. One which has the sum going from k equals 1 to the rank, and then the rest of it associated with going from the rank plus 1 all the way to m. So I've done nothing except to expand this out into 2 parts. And now I just write out the Euclidean norm of this vector. And I'm sorry that this is at the bottom of the page, because I realize that this is not optimal for lectures since people at the back can't see it. But I'll just tell you, if you can't read it from the back, I'll just tell you it has 2 parts to it. One which corresponds to effectively a term or a set of terms which depends on the image, f, and another which has no dependence on the term. And the term which has a dependence on the image is essentially written down as a square, and so if I want to minimize it, I can always make that 0. The other part I have no control over, and if I make that 0, I essentially get what we are trying to understand, what we're trying to derive. We're interested in trying to essentially get f, and so we get the components of f. What components of f do we get? The components of f which are projected onto the image space, because I've written down everything in terms of the image space. So I write down my image in terms of an expansion, in terms of the eigenvectors, or I keep saying eigenvectors, the singular vectors associated with the image space, and I write down the data in terms of an expansion associated with the data space. And so I get what I need, and now I want to summarize what we know. What we know is if the rank of the matrix is equal to the size of the data n, then you have a unique image, and here is an expression. All I'm going to basically point out is that is my expression. If I have now, the most important thing to point out over here is that if you look at the expression for the image, which is what we were interested in, inverting the matrix, you see that there is a dependence on 1 over the singular values. That makes sense, right? Because if I essentially think about the linear algebra problem as a simple generalization of my arithmetic problem. My arithmetic problem was I'm dividing. The linear algebra problem is just a fancy way of dividing rather than a number. I'm dividing a matrix. But if I write down the matrix in terms of its singular values, then all I've got to do is divide different components by different singular values. So it's a completely natural generalization of the idea of arithmetic division. You can ask the question, what would happen if one of the singular values became small? And you have a problem, because we have a singular value which is small, and if the data had noise, in fact, you replace d by d plus noise, the noise is going to be divided by a small number, and if it's divided by a small number, I'm going to run into trouble. Okay. So this is the heart of the matter. And this also raises an important issue, which is, why should we make the cutoff from non-zero to 0, which defines the rank, be something which is God-given? There's no reason. Because after all, singular values of a matrix can have some distribution. There can be some which are small, some which are large. Why should we make 0 something which is super critical? Because if there's a singular value which is small, I'm going to run into trouble. So that suggests 2 things. The first thing it suggests that you don't want to think about the singular value decomposition of a matrix or an operator in general. You want to think about an effective singular value decomposition. You just decide, again, this depends on your priors, this depends on how strongly you believe the data. You have to decide how many singular values I want to keep, and I just truncate. So I have the effective rank, and therefore an effective singular value decomposition. And the important message, even if the details are not completely obvious, is that there is some notion of a belief, there is some notion of a prior which tells you how much of the information that I actually get, how much of the data do I actually get, should I actually trust, and the rest of it is noise. And this is something, again, as I said, you're going to see again and again. Okay, so if R is equal to N, as I said, we have a unique image. I just told you about it, and I've written it down explicitly. If there was noise in the data, so the data is now the operator times the image plus some noise. I write down the data in terms of a description that I have already, and if I essentially take this and substitute into my approximation for f, then I find that I get the real f, and then I get a whole bunch of stuff which corresponds to the projection of the noise on the data space and multiplied by the image singular vector divided by sigma k. And I explicitly now compute for you the dependence of this approximation on the noise and on the singular value. So if the noise is small, but if the singular value is also small, the ratio of these two can be large, and that'll give you trouble. So that's my explicit calculation for what I just told you in words. The noise gets amplified by the small singular values. And again, question?
Yeah, just want to make sure I'm following the notation. So what we did on the previous slide was reduce the U, the sigma, and the V matrices to the lowercase u.
Those are just associated with the columns of U, sigma, and V.
Which are non-zero, or just the...
They're just normalized vectors. That's it.
Okay.
Yeah. And so the small u's, the small v's, and the small sigmas are just the elements or the columns associated with the matrices U, V, and sigma is just a diagonal. Top part of the diagonal, the number of non-zero contributions in the diagonal are exactly equal to the rank. The rest of it is just a block of zeros.
And so you also refer to them as singular value?
With singular values, a generalization of eigenvalues for non-zero, for non-square matrices. If you like more precisely, the singular values correspond essentially to the eigenvalues of A transpose A or AA transpose.
Okay, yeah, thanks.
Okay? Yeah, thank you. Please do continue to stop and interrupt. All right, so question. Now, if I already told you that M equals N equals R, boring. If R is equal to N and it's different from M, I can still have a unique image. But what happens if the rank is less than N? What happens if your matrix A has a smaller rank than the dimension of the image space? That basically corresponds to saying that there is a non-zero null space of A, or mathematically, it says that A can operate on a linear combination of B's. B's correspond to the image space, and still have a contribution which gives rise to 0, where the coefficients are not all 0. Okay? Basically, it says that there are vectors V so that A times V is equal to 0. And V is not 0, and certainly A is not 0. If that's the case, you now have a peculiar problem. And the peculiar problem is that I can add to my approximation that I already had, approximation I've written down over here, for F, so the approximation for the solution of this matrix equation A times F is equal to D, to which I can add any linear combination associated with the null space of A, and that's guaranteed to satisfy the equation A times F is equal to D, because A times F will give you this part, which will give you D, and A times this, by definition, is going to give you 0. Okay? Again, geometrically, what this is saying is, if there are parts of my signal which are essentially going to be associated with the null space, then I can always add any contribution from the null space to my solution, and it's a perfectly valid one. And to make a connection to what I showed you 3 or 4 slides ago, that was exactly like solving the inverse problem for the Newtonian mechanics question, where I could add to the u 1 over n cosine nt, and makes no difference whatsoever. Okay? This is the exact analog of that problem, except now in the matrix contribution, in the matrix context. So now I have a problem, because generically the rank of these matrices is small, and if it is small, I have a non-zero null space, and if I have a non-zero null space, then I have a whole bunch of solutions which are also possible, not the one that I'm interested in alone. So what do I do? So I now need to figure out how to make this better. Okay, so before I go there, I want to talk about what happens if the rank of the matrix is less than M, and M is the dimension of the data space. Now there's another problem, because if the rank is smaller than the dimension of the data space, that means I may not even get a solution, because there are certain kinds of data for which I have no way of knowing how to invert the matrix. Again, I can essentially couch this in the context of perception, but I will leave it in the context of just matrix inversion. There are certain quantities, there are certain parts of the data which have no way of being represented in the image of A, because A has essentially got too small a rank compared to the dimension of the data space. So there may be no solution, and if there is no solution, then the best that I can do is essentially get an approximation, and again, an approximation can be done using least squares. If I'm doing an approximation using least squares, it becomes part of the same problem. So what I want to do, I want to summarize now what we've done so far. So starting with this extremely simple idea that division of a number by a small number is an ill-posed problem. going from there to a simple differential equation where I showed you that. And I want to say the same issue hits us in the face when I'm thinking about matrix inversion. And so we've got to now ask, how do we essentially resolve this problem of dividing by a small number, particularly if the data is noisy? What's the answer? The answer I already told you, the answer that Tikhonov told us, is to say, I must have some other norm, some other way of evaluating how well I'm doing. Okay? Which means I have to introduce some notion of smoothness, which is the same thing as saying I must know something about F. All these are equivalent. Okay? How do we choose from among these many different feasible solutions in a case which is very typical, where the rank is small compared to both n and m, the dimension of both the image space and the data space? And the answer is in words, and becomes quite hard, and there are many different ways of doing this in equations. The answer in words is that we need some criterion to eliminate infeasible solutions, or equivalently, we want to build a bias towards feasible solutions. So the Tikhonov idea, which you already saw in the context of trying to ask how I should describe a smooth interpolation of slopes of functions where I'm not sampling infinitely often and where there is noise, is to say that in addition to minimizing this misfit norm or the L2 norm or the Euclidean norm, you may also want to essentially minimize some other quantity which is strictly a function of F. Okay? And F is the image itself. And that's the notion of saying I actually know something else. I know that that image is smooth. I know it's not varying rapidly on small scales. Or I may know that even if the image is not, if the image is smooth, not only is it, or I may know something not only just about the image, I may know about some operator L operating on the image. So S infinity, if you will, is some potential feasible solution that somebody told you, and I want to minimize the distance of F compared to F infinity. Or I may want to minimize the derivative of S minus F infinity. The derivative, this is, for example, L is a linear operator operating on F minus F infinity, and the first derivative will have this form. It will be essentially an upper, it will be a square matrix which has along its diagonal -1, and then just above the diagonal have a 1. So I may want to minimize the Euclidean norm relative to a default solution or the bias, or some smooth version of that. But now I have a conundrum. The conundrum is, do I minimize this norm or do I minimize that norm? And what do? You just wait there. You now say, how much belief do you have in basically the default solution, and how much belief do you have in the data? In the absence of data, I basically use the default solution. In the presence of data, I gradually start to be led by the data. Okay? Is that clear? All right. This is the idea which essentially goes back to Tikhonov, now formalized in this linear algebraic setting, which is replaced the previous formulation, which was minimizing the L2 norm, E minus AF, but now by saying I minimize a weighted function, which is the sum of the L2 norm associated with the misfit, and some regularization term which characterizes how smooth or how rough the solution should be, where the critical quantity is this parameter lambda or lambda squared, because lambda squared is always positive, called the regularization parameter. If lambda is equal to 0, then I recover least squares, the original version. But least squares is very sensitive to noise, in particular if there are singular values which are small, because I'm dividing the noise by a small quantity. On the other hand, as lambda becomes infinity, then the misfit essentially plays no role, because I'm weighting very strongly the deviation from F, deviation of F from this prior, this bias towards F infinity, and so I ignore the data and I just focus on the prior. Okay? So this now is the analog of what I told you before for how to essentially estimate the slope of a function, but now generalized to a linear algebra function.
So is the reason why we call this roughness because we have a prior for like low polynomial functions?
Exactly. Yeah. Now you have to decide, or somebody has to decide what variation do I use. So in other words, do I want to look at function? Do I want to look at slope? Do I want to look at second derivative? And then how strongly do I want to potentially bias it? Both those are very important. And those things I can't tell you. You have to decide. The user has to decide. There is a priori, not an immediate procedure. Okay. So now I want to show you something that happens, which again, from the arithmetic problem, you already see. So the arithmetic problem, I want to divide a number by a small number. What do I do to essentially regularize that? Because I don't control the small number, I just add to the small number another small number. But that number I control. And if I control that number, it doesn't really matter what the previous small number is, because that other small number that I control is always never going to be smaller than critical value, so I can always be sure that the function remains under control. And I want to use exactly the same idea over here. So if I rewrite this, the solution, not rewrite, I write the solution of this minimization problem in terms of trying to characterize f. What I want to do is minimizing that would be saying that I want to take the derivative of this function with respect to the quantity that I'm trying to essentially find, which are the f sub k, the values of the unknown elements of the matrix F. Then this 2 norm is lambda squared times f minus f infinity times L transpose L times f minus f infinity, because it's just L times this multiplied by its transpose. And similarly, the same thing over here, which I've written down over here, equal to 0. Take the derivative of that with respect to f, and you get an equation which is this. Previously, I didn't write this out, previously we had AF is equal to D, or in the squared version, A transpose AF is equal to A transpose D, because A transpose A is a square matrix. A is rectangular, but A transpose A is a square matrix. And the more Penrose inverse is the inverse of essentially A transpose A multiplied by, the inverse of that multiplied by A transpose. Now what I've got, because I've regularized this, I've got an extra lambda square times L transpose times L times F infinity on the right side, and I have an extra lambda squared times L transpose times L. If L was identity, so I'm not worried about smoothness of derivatives, I'm simply worried about smoothness of the function itself, that is called Tikhonov regularization. Okay? And if that is identity, then you see that I have A transpose A plus lambda squared times the identity. And now I've done something very nice, which Tikhonov essentially told us, which is that no matter what the singular values of A are, so therefore singular values of A transpose A would be sigma k square, I add to those lambda square. So even if sigma is going to 0, if my regularization parameter is large enough, if my lambda is large enough, lambda square plus sigma k squared never goes to 0. And so when I divide, which is what I'm doing, morally when I'm solving a matrix equation, all I'm doing is dividing. And if I divide, I don't care now because I'm never going to be able to divide by 0, because even if sigma k becomes small, or even if it's equal to 0, I always have lambda to control. Okay? So I hope that you're seeing this very simple, almost stupid thread. If I want to divide, I want to make sure I don't divide by 0. That's it. That's all there is. And the rest of it is formalism. Okay? So, in fact, if I want to write that out explicitly, so what we want to do is now solve this problem when L, these waiting for the preference or the prior is identity. I want to solve this problem now rather than the previous problem, which is A transpose A times S is equal to A transpose D. Now I want to solve this regularized problem. How do I do it using singular values? I use the singular value decomposition. I stick that in here. There's a little bit of algebra which I'm not going to walk you through, but I'll tell you the result because the result is extremely intuitive. The result is that the components of F now are a weighted average of the data and the prior. And what are the weights? The weights are the ratios of the singular values divided by square of the singular values divided by the singular value plus regularization. Note that sum of the weights is 1. Note further that whenever I have data corresponding to all elements where I have positive non-zero values of D corresponding to the rank of the matrix, corresponding to everything where I have rank R, my solution is dependent both on the data and on the prior. While for the places where I have no way, so previously remember that I said that if I have a matrix which has deficient rank, R is less than N, I could always add a linear combination of the null space vectors. And I didn't know how to do that. Now I say every time I have to do that, in fact, I throw out the contribution from the null space and I essentially use the prior. So wherever I have data, use it. Wherever I don't have data, use the prior. Okay? So in the data space, use the weighted sum of the data and the prior. In the null space, use the default solution. The additional thing that you see is that when the singular values are large, compared to what? Compared to the regularization parameter, lambda square over lambda square plus sigma square goes to 0, which means wherever the singular values are large, corresponding to the long wavelength parts, which is where the signal is, you depend on the data. Wherever you have high frequency bits corresponding to small singular values, you basically are not going to be dominated, you're not going to be dominated by this term. So if sigma is small, then compared to lambda, this term is going to be much smaller than that, and so you're going to be biased towards the prior. Okay? So the intuition that you have is wherever you have information that you trust, long scale, large time, you believe the data. The high frequency parts, the small scale parts, you don't believe the data, you basically just throw out because it's likely to be noisy.
Where's this notion of high and low frequency coming out in this?
High and low frequency corresponds to whether the singular values are large or not. So large singular values correspond essentially to eigenvectors which are varying over the scale of the system, or singular vectors, which have non-zero components over the entire system, while the small singular values correspond to things which are essentially varying over individual bits in the matrix itself, so on very small scale. So large singular values is large scale, small singular values is small scale. And so wherever you have small singular values, you switch to the default. Wherever you have large singular values, you use the data. Okay? All right, so noise is no longer amplified. The last bit is now to ask yourself, how do you choose lambda? I told you that if lambda is large, you are biased towards the prior, you is biased towards the default solution. If lambda is small, you're biased towards the data-driven solution. And there is a rule of thumb, which we sort of know, which is indicated using this plot, and I'll show it to you in the context of an example in just a minute. Okay, so what's plotted over here, the vertical axis is the prior. Okay, how far am I from the default solution? So as I go further and further up, that's bad for the prior, which means the prior doesn't matter. I'm dominated by the default. So I'm dominated by the data-driven solution. The horizontal axis is the misfit. So small values of D minus AF correspond to moving towards the origin, but as I move towards the origin, I'm very susceptible to noise. And large values of this are associated with essentially dominated by the prior. And so typically what you find is that if you plot the prior norm relative to the misfit norm, for small values of lambda, you're here. For large values of lambda, you're over there. And there typically is a very rapid change in many, many problems. And you want to pick the lambda associated with this rapid transition, because too small a value of lambda, you're too susceptible to noise. Too large a value of lambda, you're ignoring the data completely. You're using only the prior. And so in this sweet spot, you're essentially not susceptible to noise on the one hand, but you're still being driven by the data. Okay? All right, so I want to actually show you now an example from blurring and de-blurring, and I'll just walk through this relatively quickly. So imagine that I have a set of pixels, which essentially characterizes on a grayscale an image. And I take this pixelated image, for example, if I basically have a particular location, I have particular value of intensity, which is non-zero only at one location and zero everywhere else. And now I blur it. When I blur it, I basically say that instead of having only one pixel, I also have it at some neighboring pixel. Okay? So I take the image and I convolve it with this blurring operator. So that's my actual image, which is a delta function associated with being non-zero at one location and being zero everywhere else, with coefficients which tell me essentially at which locations the pixel is non-zero. Okay? And I have this blurring kernel, and if I essentially operate with the blurring kernel on the actual image, I get my data. Okay? So this is my matrix, this is my image, and if I basically operate the matrix on the image, I get out my data. So written out explicitly in the formalism that we just had, y is x convolved with h, or in matrix notation, ax plus the noise. And here is the image. Okay, after being given, start with text, you blur it, and you can barely read it. And now, you basically first try to invert that image, just bare hands. When you invert that image, this is what you get. Okay, it doesn't really matter how you did it. You just invert the matrix using, for example, using MATLAB and singular value decomposition, and you get a mess. You now do what I just told you, use Tikhonov regularization. With lambda equals, I can even barely read it, 0.1. No real improvement. Lambda equals 1, not really much better. Lambda equals 10, maybe you can start to read it now. Okay? I hope you can read it. Lambda equals 100, and I'll start reading. The ill conditioning of problems does not mean that a meaningful approximate solution cannot be captured. Rather, it simply means that linear algebra cannot be used in a straightforward way to compute such a solution. Instead, we need to have more sophisticated methods, and the sophisticated method is the Tikhonov regularization. You increase lambda even further, and now what happens is that you're essentially biasing towards the priors, you're starting to smear out things more and more. And if I actually plot on the vertical axis the prior norm, and the horizontal axis, the data misfit norm, you see exactly what I showed you before, this L-shaped curve. So here, in this zone, the data is not telling you anything. It's all driven by the prior. While here, the data is telling you everything, but it's too susceptible to noise. And somewhere over here, you have the best of both worlds. And so lambda equals about between 10 and 100 is where essentially you're doing much better. And I'm sorry it doesn't show up as well again on the screen. Typically a resolution. Okay, question.
What would be a prior, for example?
In this particular case, I'm glad that you asked me later. I have forgotten what the prior was over here. It's something very innocuous. It was just basically the prior was a uniform grayscale, because what you saw previously was incredibly jagged,
Smoothing out.
and you're just smoothing it out. That's it. It's something very, very innocuous. So you're just switching from the super jagged to tabula rasa. And in between is where all the interesting information is. Okay. All right. So I want to finish in the next 10 minutes or so by basically telling you how do I recouch everything that I have told you, which is at the end of the day just a division problem, at least in linear algebra. It's just a question of inverting a matrix, easier said than done. How do I think all this now in a probabilistic context? Why do I want to think about it in a probabilistic context? Because if I can start to think about it that way, then I may have access and recourse to a whole bunch of other tools to solve this problem. Linear algebra, I want to invert matrices. In probabilistic context, I may be able to essentially use stochastic methods. I may be able to just sample. And by sampling sufficiently and sampling cleverly, maybe we'll do a better job. So it's useful to ask whether there is an analog. Okay, so what is the probabilistic analog to inverse problems? Again, I rephrase the problem. I just changed my notation. Rather than A times F is equal to D, now it will be Y is equal to CX, or in the nonlinear regime, Y, the image, is equal to some operator, F, which could be associated with the optics of the eye and all the processing that happened afterwards, operating on scene, which is what I'm given, plus noise. So the forward problem in the probabilistic setting is to find the probability density of y given the probability density of x. I'm not now couching this in deterministic language. In the probabilistic language, given the scene, find the image, but rather than find the image, I'm saying find the probability distribution of the image. Okay? So that would be written down as, so if f is a probability density, then f given x, given the scene, find the image, would be the probability density f sub n for, I will tell you in a minute, a Gaussian, a multivariate Gaussian, of n being equal to y minus of x. So n is the noise. I need some distribution for the noise, and that distribution for the noise will essentially tell me what probability distribution is for the forward problem. You give me the scene, and I will tell you what the image is. And I'll give you the image not as a deterministic quantity, I'll give it to you as a probability distribution function. The inverse problem would be to find inverse probability density. Given the image, find the scene, or equivalently, in the language of probability, conditional probability, given this image, tell me the scene. Given y, please tell me what x is, which in the deterministic case would be inverting that. Everybody with me? Okay. How do we do this? How do I go from a conditional probability of y given x to find out the conditional probability f of x given y? I think everybody over here knows the way you do it is to use Bayes' theorem. You basically can use the idea of going back to Bayes, which says that f of x given y is f of y given x times f of x divided by normalization, which is f of y. Okay. There are names for these things. F of x is the prior. What does that mean? In the absence of any information, what is it that I know about the scene? F of y given x, which is the forward probability density, is called the likelihood, which is the ability of you to have some sort of model, which is given the scene, what would be the image, and the left side is called the posterior, and f of y is just the normalization factor. Okay? So the Bayesian approach to inverse problems is to essentially try and ask, how should I find, what should I do in order to maximize the posterior, or if the likelihood was a constant, if the prior was a constant, I want to just maximize the likelihood. And typically, because maximizing the likelihood and maximizing the log of, because the logarithmic function is a monotonic function, you typically use the log. It's easy, much easier. Why the log? Two reasons. One, it's monotonic. Two, because if I have Gaussians, then I have exponentials, and logs of exponentials are nice things. It's algebra. Okay? All right. So the Bayesian approach to these inverse problems depends on whether I have uniform prior. Maximizing the likelihood is good enough, because that's the same as maximizing the posterior. And if I have a non-trivial prior, then I really want to maximize the posterior. How does this relate to everything that we've seen? Okay? So maximizing log of f of x given y will be, there's going to be a constant which I will get when I take the log of that, which is what I have over here. And then there is a notation which will become obvious as soon as I show you the next slide. You have two contributions, one which is the log of this bit, the likelihood, and the other one which is the log of that bit, which is the prior. The log of the likelihood is called the misfit, because that's telling you about the model. The log of the prior is called the preference, because that's telling you about how much I trust what I actually know. Okay? So, in general, you want to essentially maximize this quantity. I've already told you that maximizing this quantity is equivalent to minimizing the misfit, or minimizing some combination of the misfit and the preference, depending on whether a prior matters. I want to finish now by essentially working through this for the same problem that we did deterministically, which was D is equal to AF plus N, but over here written slightly differently is Y is equal to CX plus N. Okay? So if my noise distribution is a multidimensional Gaussian with zero mean and a covariance matrix gamma, then f of y given x, f of given the scene, what is the image, the forward problem, is f of the noise, which is y minus cx, because that's my model, because I have a linear model. And if I have a multivariate Gaussian, then this is my distribution. So 1 over 2 pi, the n over 2, n is the dimension, the determinant covariance matrix, and you recognize this is just your usual Gaussian, except now written down in vector matrix notation. Okay, that's my likelihood, and you will see immediately that if I take the log of this, and I take 2 times that, and I multiply it by a minus sign, then I get my misfit, which is this quantity over here, and you should recognize this. What do you recognize this as? This is just least squares. Okay? In particular, it's least squares up to this factor gamma. So if I had independent, identically distributed random variables, then gamma will be a constant in the diagonal, which I can pull out, and that constant will be what? Will be just the variance. Okay? So if my noise is identical, independently distributed variables, gamma is the variance times the identity, then this quantity will look like that, and up to the constant r squared, y minus cx times y minus cx transpose is just the 2 norm. So what have we seen? We've seen that minimizing the least square error for inverse problems which are linear is exactly the same as maximizing the likelihood if I have Gaussian noise. So now we've essentially been able to convert the deterministic description to a probabilistic description. And if I have a probabilistic description, now I can throw out all the probabilistic tools to solve these problems rather than only the linear algebra. So there are a couple of assumptions, as I said, the key one being that I'm assuming that I have a Gaussian noise. Okay. What happens if there are singular values? Same question that I asked before. In particular, what happens if I have singular values of C which are small? Again, I have an ill-posed problem. Again, I have to basically think about regularization. And now what I do is, instead of essentially maximizing likelihood, I say, really what I want is f of x given y, and f of x given y is f of y given x times f of x. And what is f of x? It's my prior. It's what I actually think the scene is. Somebody told me, or I had experience. Okay? So I need now to build in the fact that my prior is not uniform, that my prior is essentially localized in some region associated with a particular scene. Does that make sense? Okay, so how do we do that? We basically say, again, for simplicity and for a reason that's becoming even more clear mathematically in a minute, I basically say my prior has also got a Gaussian distribution with a different covariance, P, and now I calculate the log of this quantity multiplied by 2, and I have just the exponent showing up, and maximum posterior estimate would correspond to maximizing E minus S, where E was the misfit part and S was the preference part, and this is what it looks like when L is identity. If I now compare that with this quantity, what do you see? This is now the Tikhonov regularization problem. Tikhonov regularization problem basically said, I want to minimize a weighted sum of the Euclidean norm, which is driven by data, and smoothed out prior norm depends on how far I am from a feasible solution, and the regularization parameter is lambda. And you look at this, and you look at that, and you see they're essentially identical. Okay? What does that say? That, in fact, Tikhonov regularization for linear inverse problems are identical to maximum a posteriori calculations using Bayes' theorem if my prior is Gaussian and if the noise in my linear system is also Gaussian. So again, what I'm showing you, this has been known for a while, is that the deterministic problem has a perfect analogy to the probabilistic problem. And again, I can start to deploy the tools that we now have at our disposal to solve the probabilistic version rather than the deterministic version. Okay. I'm just about done, more or less, I think, as we planned. So really what I've done is to tell you one very, very simple thing, that dividing by a small number is a bad idea, and if I want to essentially get around that, I need to make sure that I control what I divide by. And the idea of controlling what I divide by is the idea of smoothing. And so there are these two things which are constantly battling every time I'm solving an inverse problem, is how well I want to essentially invert, or the accuracy metric, and how smooth I want the solution to be, which is saying something about priors. Somebody has to tell you that the solution should not have all these jagged edges. If there was signal in that, you smooth it out, you lost it. You have to have some notion of how much belief there is in that part. Okay?
Sorry?
Yeah.
Given the equivalence, is there an intrinsic advantage or disadvantage of assuming a deterministic or stochastic setting? Or
I think with the advent of a lot of compute-powered stochastic approaches are going to become a lot easier to explore, especially if you don't know how to do it. You know, you don't have a good way to essentially invert. A priori, no, but there is a bit of caution that needs to be drawn. In general, all these problems that we are thinking about have noise. So either the deterministic case where you sort of think of noise as an afterthought, or the probabilistic view where the noise comes front and center. There is a key assumption that was made, and the assumption that's made is that the noise is well behaved. In other words, Gaussian, and it's not got fat tails, and essentially has all kinds of nice properties associated with having an expectation value and a variance and skewness and so on and so forth. So is that true? In many signals, it's not true. And if it's not true, you've got to revisit everything. And unfortunately, solving inverse problems is still a bit of an art as soon as you go beyond this very, very simple-minded framework. I mean, this is a very powerful framework because it allows you to move around and make connections. But if I have, as I've written down, and that's where all the dragons are, how do I essentially do this recursively? How do I use this with learning? What do I do with nonlinear problems? What do I do when I have non-Gaussian noise? And what do I do if I start giving up the norms, the L2 norms, if I give up the Euclidean norm? It's very much part of navigating through this territory that we are in the midst of right now. So I don't have a precise answer, except that it depends on the kind of piece. Okay?
Yeah, regarding the problem of dividing by a small number, so unless you actually divide by zero, the solution is still continuous.
Indeed.
So,
but finish your question.
Yeah, so I'm just thinking maybe you should speak about how well is a problem formed, and not just is it. I mean, according to the definition.
The definition of ill-posedness basically says that if I have small changes in the data, will I get small changes in the solution? And if I get large changes in the solution, that's very bad news.
It's not exactly continuity. It's more like stability.
It is stability, but stability is defined as continuous dependence on initial conditions. And by continuous dependence, what I'm saying is what is the slope associated with the changes in the solution for changes in the data? That's intimately related in this problem, even though I didn't indicate it, the condition number of matrix. Okay. So yes, they're all connected, and we just have to be careful in the line. Andrew.
I guess just to play devil's advocate, so what's small, right? So say I have something that looks diagonal, but every entry is 10 to the minus 10, right? In that case, small is relative, everything on there is small, but maybe if I'm dealing with something that 10 to the minus 10 is like,
Good.
really small
Yeah.
unit, I don't care,
Yeah.
right?
So what is small is defined in terms of a parameter which I should have introduced, which I didn't, which would be the ratio of the largest singular value to the smallest singular value. Okay? Because that's what really matters. If all the singular values of the order of 10 to the minus 10, I just divide by 10 to the minus 10 and I'm good. But what really matters is how much amplification happens at different scales. That's precisely what somebody asked me, this length scale thing. Large singular values are associated with large scale features of the scene. Small singular values are associated with small scale features of the scene. The hair on my head or whatever little is left and so on and so forth. So what really matters is the condition number, or equivalently sigma 1 over sigma r, where basically are looking at this. Yeah. more, yeah.
I have a question about the notion of stability.
Can you speak up, please?
Yeah, sorry. I have a question about the notion of stability. I don't think this is up to linear systems, but like, you have a system where like you have qualitatively different behavior depending on initial conditions. You get discontinuity in solutions, but only not everywhere in the space, just like in a part of the space. Is that an well-posed problem, like a bifurcation, for example?
Very good. Yeah. So a bifurcation, right in the neighborhood of the bifurcation, the dynamical system, you don't have a strict notion of stability according to what I just said. However, what you can do is something called unfolding the bifurcation. So you ask which modes are the ones that are growing as you move through the stability, instability, pull those out and look at the remaining part. And so you essentially use the fact that hopefully everything doesn't go berserk on you simultaneously. By everything, I mean all scales. There is a particular scale on which things happen. If that's the case, you pull that out and you look at the rest of the system and then you deal with it separately. You just basically break up the system dynamics into a part which is varying rapidly associated with the growth of instability and the rest. As long as you have this separation, as long as you have a small number of modes which are going unstable, a small number of nodes, meaning, so for example, if I had everybody milling around in this room simultaneously, compared to just a few people moving out, the first is much harder problem than the second one, because I don't have necessarily scale separation. If I have scale separation, you can use the same ideas, but essentially break up the problem into little bits, and then I fight into each one separately. And if I'm being vague, I'll sit down with you afterwards and essentially slightly more precise. There was another question somewhere. No? Now, probably this is a good time for us to take a 5-minute break, and then we will continue with Tommy, talking about generalizing from this in the context of machine learning, supervised and unsupervised.
Using this.
Yeah, exactly. Okay?
Yeah. I don't know. So I have to be a hunter on Monday. So I'm hanging out, but I'm coming back on Tuesday. And so there's students, and I don't think I'm going to take part in one of the projects here. So there's more people. And then I think my family's going to come up on Wednesday and Thursday. I have two 18-month-old twins that have never been away from the house. So this will be their first time in a hotel room. So this afternoon I'm going to go find a little hotel down the road somewhere. I've already talked to them and have them come up and play on the beach and go to the aquarium and stuff. And that works out. And this sort of stuff that was mostly to come for like the neuroscience. So, because I know the brain has neurons. I mean, this stuff I'm sort of familiar with. But the brain has neurons, and that's about as far as my knowledge. I'm William Sack. I'm the chair of the department at Colorado. And we're, together with Wells and a couple of other schools, are going to be developing what is... No, it's not board. I actually have a question about this for you. So I'm a computational language, right? And there's computer models in the way like 1.5 to 3 years old. It's pretty well known that the relationship between grammar and the languages that generate is not smooth. So a small change in grammar is going to generate potentially a large change.
I'm talking about the relentless problem, the slower problem.
Right.
Very, very hard.
Yeah.
That's extremely relentless. Application. Application. Maybe that's easy for that. I have to you give me the temperature. Now I have to predict backwards. You can't do it. Find it hard.
Yeah, the question of acquisition is the inverse problem, right? So that's what the kid is solving, is the inverse problem. Given the strings of the language, what's the grammar? I think, depends on the psychology, right? I mean, it really depends on when the kid is actually, once they argue enough, or have argued, there has to be a base amount of maturity in the brain before the kid starts. The problem of solving things, right, which is completely honest. Right. Somebody aligned yeah, exactly. So they're like really fast.
You make changing small things a little harder.
Where does the measurement come from? Right. Oh, you're comparing your current hypothesis with your next hypothesis.
I've been using it for a while now. It's pretty fast. You have to compile it and then look at it. I don't know, every time the type of set up to compile it, so I have a program called yeah.
Depending on what you do.
You haven't used all that anymore now.
So actually, there was a theory in the late 1980s, the early 90s called the little linguist theory of acquisition. There was kids actually have little linguists in their head, and it's being effective at there's a current hypothesis, compared to the next hypothesis is. So
But it makes the file in my life, I can't remember all my directions. Depending on what.
right. Just metaphorically, it's an interesting.
So how long do you I'm trying to feel like doing. It sounds like a
or your neuro program, whatever, computer science, and they're really well equipped, so to speak, to have the ability to power. That is very hard, but I'm hoping that we will see that again and again. I only learned much But I found most of the well, I don't know. So, yeah, I think it's a problem.
I'm worried about being that massive part of it, about creating the new program in data science, right? And that's essentially try and sort of delegate a lot of that work because I'm more interested in doing leave it in perspective. But I think it would be good to support it. Remember another year. But I'm more interested in this. I'm trying to get a higher environment. So maybe we can all after the semester starts, have people announce New York, half a dozen, not 20, have an outline of what might be automatically or reasonable level without having to include any of it. I don't exactly why it's I don't know if it's I think we can do that right now. It's kind of effectively doing it. We don't only pursue the later. You know, I don't know if actually what happened. Anybody can take it pretty much from any history. Like I believe it's in there. So it has to do with so they still think I have a feeling we're going to get a taste of that tomorrow, looking at Josh is going tomorrow, so it's going to be
So let's first make a small poll. This is about a MATLAB refresher, possibly this afternoon. How many of you have computers with MATLAB? Can you raise your hand? Oh, wow, okay. So it should be fine, because we have some computers coming, certainly on Monday, maybe by tomorrow with MATLAB, but we can start looks like we have enough, right? So when would be MATLAB? That's optional. Okay, good.
Is there a solution to people who have computers without MATLAB?
I think so, right? Yeah.
Yeah, I think we'll pair people. Is that the idea?
Even a group code we can download and use one of the lectures from the file. I mean, the easiest way is to group people to take before. That's the easiest way. Otherwise, it will be work the lesson. Yeah.
So I think we ran a bit over, and we're constrained by lunch, which end at 1, I think. So let me be a bit faster than I would have liked. This is kind of an introduction to what we need for tomorrow about supervised learning. So there are different, learning is a big word. There are different types of learning. Here is only a partial list. Tomorrow we see some more. Today I'm speaking only about supervised learning. Okay, you have examples which are input, output, X and Y. You are trying to learn a relation, a model, a theory, a function that will allow you to predict new output for new inputs. And one of the themes, as we saw today, for learning is well-posedness and generalization. So you heard about well-posedness. I'll tell you more about generalization, which is another word for prediction, for predictability. And these are, so between today and tomorrow, you'll hear quite a bit about ideas that are at the core of this classifier, regressors, RBFs, support vector machines, and so on, which are stuff that works. These are the kind of things that are used in many of the applications I mentioned earlier, like the Mobilize system. So I'll tell you only about the first two parts. The third one will be essentially tomorrow. Just some basic concepts on in supervised learning, and then just an overview, an idea of the foundational results. Some of them are quite philosophically deep, have to do, if one wants, about the nature of science and what is scientific. So the problem of supervised learning, as we said, you are given a training set, and that's a number, possibly very large, of input-output pairs. And your goal is to find a function which depends on the training set, so it change as you change the training set, which can predict Y for new X. Okay? Now, for this to be, does not always need to be possible. It may be impossible. There must be some relations between X and Y for you to be able to make some prediction. For instance, one counterexample I have, suppose I give you as inputs, names of people, and then as outputs, I give you their telephone numbers. And I can give you as many examples as you want. Telephone book after telephone. And I bet you cannot find an F that can predict the telephone number given the name, right? It's more or less completely random function. If somebody is willing to try the experiment, let me know. So that's a kind of notation. We assume that the training set is drawn with a IID, and so it's independent and identically distributed variables, random variables, and the identically is a crucial assumption. And there is a probability distribution, but you don't know it. What you have is only this training set, which depends on the underlying probability distribution, but in a way you don't know. So you don't know the probability p x comma y. If you know that, the problem would be solved. Okay? So you're trying to infer something without knowing this probability distribution, but only samples out of. You know, for instance, if you know this py of x, that's really what you'd like to know. Now, we assume there are probabilities in general, because even if the underlying process is deterministic, there is certainly noise in the measurements, or the underlying process may not be deterministic. So there are many different cases. For instance, suppose this is the deterministic relation between x and y, sinus wave. So if the probability distribution as for p of x, for your input part, as below, then this means you're getting many more samples where there are peaks in the probability distributions and very little elsewhere, or in this case, vice versa. And so there is always noise involved. For instance, you know, if you, let's see, let me use this blackboard for a second. If you have, you know, a spring, and you have Hooke's law that the force depends linearly on the extension of the spring, then the probability of f given x will be a delta of f minus a of x, no noise. Okay? But if you have any noise, like additive Gaussian noise, then this probability will be a Gaussian in the error. So, there is a key thing you want to do in learning, which is you want to make predictions. You want to generalize. And this is kind of different from traditional explanatory statistics. Just don't simply, you're not happy just to explain the data, but you want to use the data to make predictions. The ability to generalize is also closely related to overfitting, to avoiding overfitting. And now, if I want to measure how well I'm generalizing, I have to first decide about how I measure the errors. And so, typical notations in machine learning is to use this loss function that measure the error between your prediction and the actual true value y. So, the usual loss function, the traditional one, the one we have seen, for instance, with I had the one before is the square loss. There are two loss, but there are other choices, like for instance, the absolute value or the so-called epsilon insensitive loss introduced by Vladimir Vapnik, and I think I may have, let's see. Yeah, so for instance, this is the quadratic loss, here is the error, and this is the absolute value, and this is the epsilon insensitive loss. And this is all in the cases of regression, which y can be a real number. Now, in the case of classification, when y is either 0 or 1, then I can have the other types of losses, which are, one is the hinge loss, which means you pay a lot. One, if you are wrong, your sign is wrong in your F, or you pay this is the analog to the square loss. You pay the square of your error. So y is 0, 1, and this is what you pay. And as you can see here, this hinge loss, which is the positive part of this error, 1 minus y times f, y times your prediction. If you look here, you see that in the hinge loss would be this kind of loss here. So they are all closely related. They're kind of one an approximation of the other. But for instance, when we see tomorrow this square loss regularization and support vector machines, the real difference, they are very similar to each other. The only difference is a different loss function that they use, square loss versus the hinge loss. And this gives rise to a different optimization problem, but the basic structure of the solution and the basic properties are exactly the same. So, now, how can I define generalization in a quantitative way? The key notion is the one of expected loss. So this is the expectation, this is the unknown probability distribution, this is my loss function, think of f of x minus y squared, for instance, and this is the probability distribution. If I would have the probability distribution, this is the measure of the expected loss, what I would expect in the future, in the average. And so this would be very ideal if I want to measure my future error of a function I have. Suppose I have an algorithm, I'm a hedge fund, I want to predict the market tomorrow, and this would be the expected value of, for instance, how much I'm losing or making tomorrow, right? So the error I'm making in the average in the future. The problem is that I don't have the probability distribution, as we said. So if I would have the probability distribution, of course, a good idea would be to find the minimum of that loss, to find the f, the function that minimizes the error that it predicts best. This would give the what sometimes called the target function, the minimizer of the error, the best function. Now, so these are, in summary, the distribution I don't know, the training set I label n because that's the number of examples it could change. This is the loss function. This is the expected risk. And this is what, since I don't know this, a proxy for it. Is the empirical risk, is what I can measure on my training set. I have these n examples, and I just take the loss, so the difference between the prediction, according to the metric, to the loss function I use, and the actual true value, and I take the average of that. Now, and using this, I could, using this proxy, I can measure this empirical error for a specific function, like, so I take an f, and I can try also to think, well, I could minimize it. That's the most natural thing. Look for the f that minimizes this empirical. Now, the key question is, if I want to do this, for instance, again, I'm a hedge fund. I found an F from past data about the stock market. I find that this is the error of the past. I find it's pretty good, doing well. But what I would like really to know before I bet $1 billion on this, I want to know that this empirical error that I measure is actually a good proxy for the expected. This is the kind of warranty that I want to know on my algorithm. I want to know that as I increase the number of data in my training set, the probability of the difference between the two being less than epsilon is very large. And of course, I would like to know, in reality, some bounds on n, for how many data I need to know to have in order to have this epsilon in that and delta be good enough to bet $1 billion. Okay, so so it turns out that that minimization problem, finding the best f just from the empirical, minimize the empirical error, is actually not even is not well defined. It's completely imposed. I have to define the space of function over which I do the minimization. What is the set of models of functions, of relations. And so this is called the hypothesis space. And the intuition is that I have to restrict this. I cannot allow everything to be there, right? I have to say, which is the class of functions, of models, of theories. Turns out this is, restricting this appropriately is the key to making the problem well-posed and simultaneously also to have predictability. Okay? So, for instance, I could restrict this space to be linear functions or polynomials. How many of you know what a Sobolev space is? Okay. In a Sobolev space, you define it in terms of norms of derivatives, bounds of the norms of derivatives. You don't really need to know, but I'll give you a little insight later. There is this tight relation between restricting the hypothesis space appropriately and smoothness of the functions that are in this hypothesis space. So let's look at this class of algorithms which are called empirical risk minimization, and I already described what it is. It's finding an F that minimizes the empirical risk, and the key is here is to define the space of function here, H, in such a way that the problem is well posed and gives you the function that can predict. So that's again repeating what I want. I want a function that minimizes this proxy for the expected error, is the empirical risk. And what I would like to have is generalization. So for the number of examples that goes to infinity, you want to have that this proxy becomes the same as the expected error. And I'll give you an example. It seems something kind of trivial, but it is not. In most cases, that's not true for H arbitrary. For instance, you'd say maybe if F is a well-behaved function, like continuous functions, that does not work. So you need something more in terms of which hypothesis space. So you want that, and you also, of course, well-posed essentially stability. Again, if I'm a hedge fund, I have used historical data on the S&P for getting this algorithm that predicts whether tomorrow will go up or down. And, I find that if I perturb a little bit, one of the component of my X vectors in the example, so for instance, one of the components is the closing price at 4 p.m. every day of the NASDAQ. That's one of my regressors. I perturb it a little bit, and the function I get out now as a predictor changes a lot. Well, that's very troubling because the closing price is quite noisy. So you want to have stability of your solution. And so this is really the key property of well-posedness that you want to have when you solve, for instance, your minimization. So, of course, you want to exist unique. These are typically, you can ensure those, but this one is not trivial at all, and it's key in learning. Those are the two conditions: generalization, stability. Here, example. Suppose again is the one-dimensional case of function interpolation or approximation. Actually, you have some sparse data, and suppose these are samples from this function. Now, suppose you have your algorithm giving this solution, and the question is, if I get more data, will it converge to the correct solution? This is a condition for generalization. That's a case where I have 10 samples. My hypothesis space is polynomial of the 10th degree. So it fits exactly the data because it has enough degrees of freedom. But when I perturb the points slightly, the solution changes a lot in certain points. It's very unstable. If I restrict, make this hypothesis space simpler, so now you have degree two polynomials, then I don't fit exactly the data, but the solution is much more stable when I perturb. So now this is an interesting question. There is a lot of learning theory, typically Vapnik and others, have been concerned about the problem of generalization, predictability. But independently, and so one of the conditions that is known guarantees generalization is for the hypothesis space to be compact. And I tell you in a second what it is. And it turned out that it was well known since Tikhonov that the same property guarantees well-posedness in many problems. So the question was open until a few years ago is whether or not these conditions of stability on one hand and generalization on the other are related or not. It turns out they are equivalent under the appropriate definition of stability, which is, I find, very interesting. So if you ensure one of the two, the other is automatically false. Both of them. So, in a sense, it's easy to see in the case of let me see if I can let me give a feeling for, okay. So if we look at this problem, one could think, how can I have an H space of function that could do a reasonable job, that could ensure stability and generalization. Let's say generalization. One could say continuous functions, but as you can see, I can make many, an infinite number of continuous functions go through those points. Right? So continuity by itself is not enough. Now, On the other hand, if I impose some condition of smoothness, the intuition is, if I, for instance, say that the interpolated function cannot have, say, a derivative which is higher than something at any point, then the intuition is this may do the job. Certainly restricts the number of functions I can put through the. And there is this definition, this property of a space of function to be compact, and this means, can you see actually?
If you have white chart.
Okay. That's a good idea. Thank you. So, so that's my space of hypothesis. There are function f in it, and if I have that f is uniformly bound, if for all x, all f are such that f of x is less than m for all x. Okay, they cannot be larger than some x. And then if I have that f is the space H is equicontinuous. Anybody knows what it is? Okay, you know what continuity is. So f is continuous if for any, let's say, any delta, there is an epsilon such that I can take x prime minus x2 less than delta, and then f of x is less than epsilon. Okay? And if this is true for, I want this to be true for all x prime and x double. Now, this is continuity. We saw it's not enough to impose continuity, but equicontinuity means that this is true for all f in the space, uniformly. So using the same delta and epsilon. That's the trick. Now, if you have these two properties, equicontinuity, so this is for all f, and boundedness, there is a theorem from D'Arzela that says that space is compact. Compactness essentially says that, you know, this is probably the best way to describe it. Connects the space to smoothness, to how smooth the functions in the space are. Because it's like saying that the derivative, they cannot change too much. And no function in the space can change too much. Right? Uniform. There is a bound for. Yeah.
So I'm a little confused.
So the risk is an expectation, right?
Sorry?
The ERM is that's an expectation, right? And so you're looking for...
We're not speaking about minimization now.
Sorry, expectation.
Yeah, but we're not speaking, I'm just telling you which is the property of the space of functions, right?
Right, but
the hypothesis space.
So my memory is it's something like a weak star interval or something like that. Or like this isn't specific to learning, is it?
This is not specific to learning, but the condition for the empirical risk minimization to generalize. In other words, this condition here this, for instance, is guaranteed if you do empirical risk minimization in a space of functions which is compact.
Okay. And what you're doing right now is just trying to characterize which functions it's true that
I'm telling you what are, a property of the space, of a space of function which is compact.
Okay.
Space of function which is compactness is equivalent to equicontinuity.
Okay.
So that's a connection with smoothness. Why smoothness is important. Equicontinuity is very similar to, is essentially a smoothness condition on all the functions in space. Is that, you seem still puzzled.
Well, yeah, like, I guess, I do remember equicontinuity is one way of getting, like, convergence of expectations from finite, like, I'll think about it.
Okay. So, in fact, I mentioned this very quickly, the compactness is a condition which is sufficient for generalization, is sufficient also for stability, but there are conditions that are more general, that are necessary and sufficient, and this is a characterization in terms of what is called uniform Grigoryenko-Cantelli class of function. I just want to mention that you don't need it, not even for tomorrow. And there is a corresponding theorem that defines stability in a certain way, which I'm not going to tell you much about it, apart from the fact that it's something like deleting one of the training points and measuring how much your prediction changes. But that shows that the conditions, this condition of an hypothesis space being UGC is equivalent to stability. So ensuring stability and generalization are completely equivalent under these definitions. They correspond to the same constraints on H. They are both guaranteed by stability. So so now it's nice that you can get to those two conditions that you'd like to have in learning. So the ability to predict and stability with respect to the data, you can get them simultaneously. And you can look at either having a stable algorithm or restricting the hypothesis space in empirical minimization. And so, the kind of deep philosophical implication is something like this cartoon of what science is about. It's kind of starting with Newton, taking measurements of the apple falling, and try to find a law, a function that could fit the data and be predictive for future experiments. So the kind of learning theory, like Buckley or tells you in order to do this, in order not to simply fit the data but also be predictive, you need to restrict the space of possible models theory before you see the data. Okay? Only then a theory can be predictive. If you just fit the data, then you're doing astrology, but not astronomy, right? You're just explaining the data. That's often what the financial newspapers do. They tell you, today the market went down because people sold, basically. And that's not something you can use to predict tomorrow. So, but the other part of the results tells you, theories should be stable. So what does that mean? Is that if you add the new data, they should not, most of the time, they should not change much. So in other words, you cannot expect relativity theory to come very often. These are kind of tautology. Since science has to be predictive, then it cannot be violated all the time. So there is this close connection between prediction and stability. Now, tomorrow you hear about regularization, and Ma spoke about regularization, Tikhonov regularization. This R of F is a functional that you minimize together with the empirical risk. And one way to look at it is to think of minimizing the empirical risk, DRM, but under some constraints on the hypothesis space, right? For example, it could be the norm of F, this R of F. And so one way to solve a problem like this is to use Lagrange multipliers, which means minimizing something like, turns out Tikhonov is not exactly the same as completely equivalent to Ivanov, that's something, but that's one way to look at it. And so this is the connection between minimizing the empirical risk under the constraint on the hypothesis space and looking at Tikhonov regularization as a way to do this.
So, sorry, can I just ask, this is probably a clarification for myself. So basically what Ivanov regularization is doing is saying there's this hypothesis space and some parts of it are verboten, and therefore the parts that remain will ensure stability. Whereas Tikhonov is saying any part of the hypothesis space is possible, but the complexity of the hypothesis in a way is going to penalize you, pushing you more towards the stable parts of the hypothesis space.
Yeah, but just from the point of view of optimization, one way to solve this constraint problem is to solve this, thinking of gamma as a Lagrange multiplet, and solve for it, right? So
I can see now.
there are other there is another interpretation that was mentioned before in terms of probabilistic interpretation, which this is related to the prior on F, and this is a model, a probabilistic model of your measurement process. In that sense, you know, this would correspond to harder constraints. It would be easier to see the probabilistic interpretation here. Okay, so so that's essentially summarizing what I just said. You know, Tikhonov regularization and Ivanov ensured well-posedness, especially stability, and ensured generalization, and there is this close connection between ERM on a constrained hypothesis space. The story, of course, is that you have to put some constraints in order to solve the inverse problem. You have to put some constraints in order to solve the problem of learning. You have to put some constraints in order to get generalization. Constraints may be a lot of different things. It turns out that, you know, if you have very specific constraints, like for instance, you know that you have a linear mapping between input and output, that's a very strong constraint. You should use it, but if you are, you know, ignorant, then there are these minimal constraints you have to assume if you want to generalize. So, by the way, generalize, I should say that, does not mean that your solution is good. Generalization means that the empirical error, what you measure on the training set, is a good proxy for what will happen in the future. So, if I'm the hedge fund, I have to find an algorithm that works well on my data, and I want to have a guarantee on this type of algorithms that in general, then I will know that my small error training set will be within a certain probabilities, small error in future. But generalization does not guarantee that automatically what I find is a good predictor on the empirical side. I have to measure, but that's easy to do.
So is this the same sort of structure between precision and accuracy?
No, it's more a distinction. You know, one of the standard preoccupation of all the statisticians is consistency, universal consistency. And this means that in our case, this would mean that our algorithm converges to the best possible solution. You can have those guarantees here, but I think in practice, that's my personal view, much less important than generalization. Because I can measure the error in the empirical, and I do in practice all the time. What I need to know is that this is a good proxy for the future. That's generalization, it's not consistency. Okay, I think we have a window for lunch, which is 50 minutes. So it's probably better to stop here. But if you have some questions, urgent questions, ask them now. Otherwise, we'll be around for the next.